welcome everybody in this week's quantum colloquium. We have a pleasure to host Dr. Bartosz Naskrecki from Mickiewicz University and Center for Credible AI in Warsaw Institute University of Technology. So Bartosz is a mathematician, algebraic geometer, number theorist. He did his postdocs in University of Bristol and in Bayreuth. He's interested in different aspects of different applications in mathematics, also in physics. But in recent years, he got really hooked, really interested in potential applications that AI, large language models, can offer for mathematical research. And he co-authored Frontier Math set of problems that were, if I understand, designed to challenge state-of-the-art LLMs, like how well they perform for mathematics. He's gonna share with us his perspective on application, like how mathematics is gonna look with developments of AI. It's great to have you, Bartek. The floor is yours.
Thank you very much for this very kind introduction and for the invitation. So it's my great pleasure to be here and to share with you some of the ideas that I think we all share. Probably a lot of expectations and a lot of we have a lot of mistrust and maybe some kind of curious questions. So I want to somehow share with you some of the ideas and thoughts that I have just gathered in the last couple of years. Okay, so let me start maybe with a little advert. So if you have not read yet, we have written a very short commentary for Nature Physics with Professor Ken Ono. So Ken Ono is a very well-known number theorist. He was actually involved, maybe you have seen this movie about Ramanujan, this very famous genius, Indian genius. So actually Ken was one of the co-producers of this movie, and there is actually an anecdote that he told me that he was very proud when Jeremy Irons is actually playing in this movie, and he was teaching Jeremy Irons how to pretend to be a perfect mathematician in front of the chalkboard, like how to stand and how to argue and so on. Ken is now, so he worked for many years in the University of Virginia, also has like a lot of interests related to sports. So he was actually one of the reasons why American team has won several gold medals in swimming. So he kind of optimized their swimming. And now he recently joined also a startup called Axiom. So he's also deeply involved in mathematics and AI recently. And in the end of August, we just wrote a very short commentary. It's like 4 pages. So I encourage you to read. And I think the most interesting part of this commentary is the final page where we somehow give some kind of roadmap for what we expect that might happen in the coming years. Unfortunately, I would say that recently we should say rather weeks than years, months maybe. So like for many millennia, I think most of mathematics, most of organized human reasoning was really somehow centered around people gathering intuitions, getting some kind of conjecturing, somehow like really it was something that was not very well formalized. In the last basically 100 years, we got from this kind of very informal text, as you can also see, like if you read classics like Euler, you can actually be very shocked that the amount of formal reasoning in his text is very, very low. Somehow, like he was getting a lot of correct conclusions with very vague arguments, which is extremely surprising when you look from the point of view of today. So, like, what was the guiding principle that allowed him to get to this kind of very successful derivations of like his famous Euler's formula and so on? But in the last 100 years, what happened was that the invention, first of all, of the set theory and the foundations of mathematics, our Polish mathematicians were, like, for example, Tarski, were very much involved in this. And like at the beginning of the 20th century, David Hilbert gave his list of famous Hilbert problems. And this is where actually this kind of push towards formalizing mathematics, making it completely robust, started. So this is this part which I call formalization. And in the first, I would say, 50 or 60 years of this quest, which was somehow interspersed with very surprising results, like famous Gödel's theorems that say that essentially mathematics, which is very complicated, so that contains the arithmetic of integers, cannot be completely formalized in the sense that there are statements which are true in every model but cannot be proved within this theory. But these are, like, I would say, like little distractions from what actually is happening right now. So like from the beginning of the 70s, even groups in Poland, like there is a famous group in Białystok that was developing a Polish theorem prover called Mizar. That's a very famous Polish contribution to this part of science. People started to realize that if we want to somehow push the frontier of mathematics, and we have seen in the 70s already extremely complicated proofs like Veil conjectures, some things about algebraic geometry, for example, that it's necessary to somehow organize this knowledge, mathematical knowledge, in a way that it will become, first of all, modular. You will be completely sure that there are no gaps in the reasoning, especially that if we are doing mathematical reasoning, deductive reasoning, like if you make just one mistake, like with a computer program, then everything can just go broken, right? The program won't compile, but mathematics won't follow. So that's exactly the point. And now just fast forward, so this is this third arrow here. We are getting now to the very strange world where at the beginning of 2020s, we have started seeing some organized computer systems, which are called large language models, that can somehow assist and help us understand this big bulk of mathematical knowledge in a more proficient and efficient way. And now going below here, these are actually things that happened really in the last year. We are seeing already some glimpses of machine assistance in the sense that we have now a technology that, for example, can suggest a proof. There is actually a very recent publication from yesterday from one of the group in Google DeepMind and also another one with Axiom, which allowed them to actually do something end-to-end. So you have a conjecture, which you formalize, so you have like a formalized statement of the conjecture, and the model actually derived the complete proof. Now you can ask all sorts of questions, like, is this proof novel? Is it just something that it just brought from the internet, from some kind of literature? And it turned out that sometimes yes, but in these very recent examples, we actually have some golden nuggets that seem to be actually novel. So like we have now systems that maybe are not making some breakthroughs, like, you know, like designing completely from scratch something called calculus, but they can definitely deliver proofs of statements completely end-to-end. So like the amount of human work is basically close to zero. I'm going to show you one example of mine where this kind of end-to-end approach is actually completely successful. If you have in mind some kind of recent experiences with large language models like the famous ChatGPT interface, then you should take it with a grain of salt. So like I'm going to talk about systems which are hybrid. So they are not necessarily just based on LLMs. Usually the LLM part is like the creative one, the one that makes mistakes. But then you have the second part of the system, which is actually verifying these claims, formalizing them. And this is the part which is actually related to very hardcore programming, something called functional programming. And from this, we actually get concrete results. So like in the end, we actually do get something that is like a new knowledge and something that we can actually use. So now I want to end this diagram chase with these two right parts. So the upper part is this guidance. So I think we are already living in the era, maybe some people have not realized it yet, that we have mathematicians, also physicists, that are definitely like amplified by these kind of systems. I'm going to say a little bit more in the coming minutes, like what I think about this idea, like what is one of the preconditions. I think one of the most brutal requirements is that you need a lot of compute. Compute is somehow like one of the key factors that will make any of these systems work. If you think, we had a very interesting discussion with Michał before, like if we think in Poland, about doing this kind of contributions in this new world of science enhanced by AIs, we definitely should struggle to get a lot of money to somehow establish our own independent labs that will be developing this kind of tools. And I'm not talking about developing ChatGPT. We don't need that. We need tools that are based on LLMs. They don't have to be as big as ChatGPT. They can be specialized, tailored to the particular field of inquiry, but definitely it's going beyond, like, typical end-to-end grant or something of this size. It definitely needs more. It's more challenging. You need engineers, you need scientists, you also need some data scientists. So that's a big project usually. There are now a few labs which are doing this, and they are getting quite successful. They are not very big. Like the Axiom that I already mentioned, it's a lab that consists of like 25 people. Okay, so it's like we have 25 people here. So if you have enough compute and people dedicated to do this, I think we could push the frontier. That's exactly what is my opinion on this stuff. And the final bit, this is like a science fiction, but quite ironically, when we were finishing this paper, I definitely thought it was science fiction, like in August 2025. Now I don't think so anymore. So I think that we have examples where this kind of autonomous discovery in some limited extent can already happen. We definitely don't appreciate the fact that enough that there are new architectures being built, and the models that you actually experience are actually models based on the architectures from like 2, 3, 4 years ago. And the new ones are still in the labs. They are not cooked well, so they are not still visible, but they are around. So they are definitely there. I think probably it will be still a lot of place for humans, but somehow the landscape will become very, very subtle. So like being someone who just improves on the theory of the others, that's probably something that will definitely be delegated to these kind of new systems. And I don't think there will be enough space for people without genuine new inventions that will still stay on the market for many years to come. Okay, so this is just this summary. Now I want to do some little advert. So I started a few days ago a Discord, if you are interested in this kind of topics. It's called MathBot, and it's just a community now. At the moment, I think we have 140 people. I'm actually very proud because I think like at least 70 of these people have PhD in computer science, in physics, or in mathematics. So it's a very dense and very demanding society. There is no structure. It's just like if you're interested, you can just pop in and show up, and you can just maybe chat with people. And we are also building some kind of agentic systems. We are trying different sorts of tries. I don't know exactly where this is going. It's just too young, but if you're interested in this kind of topics, then I'll be happy to add you to this community. Okay, and now let me go now deep into these things that I want to talk about. Also, maybe let me just make sure that I have somewhere a phone or something. How much time do I have? Okay. I just want to be on time, so not to stretch you too much. Okay, so since I'm going to talk about mathematics, I think we need to start from really some kind of consideration of what actually is a mathematical proof and what is a mathematical theorem. Okay, so I think most of you have definitely experienced mathematics in this way, that there are some sentences written in usually language that you can understand, natural language. There are in these sentences some notions that usually are given with a particular other sentence, which is called a definition. And now to somehow play this game, what we have developed is that we have certain rules that allows us roughly to kind of operate with these objects. So like somehow express like what happens with the objects in the statements to get some kind of new interaction, new statement. That's roughly what a proof and mathematical theorem is in this kind of hand-wavy way. Of course, like if you have ever experienced a real proof, you know that there is a little bit more of the structure. It's more like, if you ever played the board game, then I think mathematics is actually very close to playing very complicated board games. You have a rule book and you have to follow these rules. maybe the rules could be inconclusive or incomplete, but you have to follow the rules to get something out of the game, and that's exactly how you can think of mathematics. Of course, there is something that is very difficult to somehow comprehend on a very definite level. It's like, what makes mathematicians think that, like, what should we put in the next sentence? Like, how do we actually make justice to the statement, which is called a theorem, by arguing like from step to step? And this is something that took mathematicians actually more than 2,000 years to get to this upper level, so that mathematics is really like at the very back, at the very bottom. It's a game where we have very precise operations that basically just transform certain kinds of text in a very precise way. In the next few minutes, I'm going to show you that this can be pushed even further. So basically, like the conclusion, and this is called the Curry-Howard correspondence, is that in a sense, like all of the provable mathematics that we can write down effectively can be turned into a program, okay? So if you have a finite proof, then it can always be turned into a kind of a computer program, and this program can be compiled. So somehow the experience of doing mathematics is like very close to the experience of programming, actually. And that really took mathematicians almost 2,000 years to notice. And in the last 2 years, what we have observed, and this is actually something that you're all interested in and came to see now, is that there is a big, I would say, a convergence between the idea that computers can program by themselves, and since they can program by themselves, they can probably also do mathematics, okay? What I think is still missing from this picture is one subtle point, is like in the programming, but also in mathematics, like every next step that you are going to write, someone has to decide what it's going to be, right? So like who is deciding, like, what is the overarching structure that forces you to actually put this specific function in the next line? What is forcing you to actually make this specific construction? So that's something that I think is not really well understood. Like somehow this kind of meta-mathematics, or like I would say like the informal part of the mathematics, is really lying between these lines. So like if you're thinking about like if you're going to lose your job because the AI models are going to, like start proving theorems in mathematics, like start deriving some new theories in physics, think about like, is it possible that these models are going to somehow also comprehend this meta-knowledge that makes you decide on the next step, okay? So there are like several layers of this problem, and I think we are still not there. So like the current LLMs and the AI technology, even using neurosymbolic techniques, is still not at the level that it can completely, from out of thin air, in a sense that we comprehend, just concoct completely new intuitions, new insights, like connecting two different notions, right? I think one of the most prominent examples is actually general relativity, right? Like somehow making someone to believe that the connection between differential geometry and some core principles of physics and fields can somehow turn into effective theory that we can make a prediction from. That's something that I think lies very much beyond the comprehension of the current systems. It's like something that we probably still don't understand and don't appreciate enough. Okay, so let me switch now to the next slide. Okay. So I want to give you just a few glimpses into what kind of mathematical thinking is really challenging for us and for AIs. I think Kepler's hypothesis is one of my favorite, because it's something that if you look at, you can immediately realize like what's going on. Like the sphere packing problem in 3 dimensions is just something about like how effectively we can populate the space with balls of the same radius. And what's surprising is that this proof actually, it took many years to write. So this is Thomas Hales who actually proved it. It took more than 100 pages of dense text. Then also the paper was actually formalized, so we now have completely documented computer program that verifies in this kind of syntactic way that this theorem is completely sound. And the question now that I raised before is like, do we have AI systems that are capable of coming with this kind of insight, right? I mean, I can definitely show you in a second systems that can derive parts of this theory basically automatically, but do we have an AI system that can look into the world and just say like, oh wow, there is something interesting about the balls, right? And I'm going to ask this kind of question. And I think this is exactly the place where the mathematical invention of humans is kind of different from what we see from LLMs. Like if I will just single out a single element of this whole race that is going definitely beyond AIs, it's exactly this kind of situation that you have a perception from the world of something and you can somehow turn it into a proper abstraction with which you can interact. Okay, if you think about all the theories that you have learned in your life, you have worked with, you are going to see that the core part is exactly the insight that is going between the interface, so the world that we perceive, and something that we turn into a useful abstraction. And this aspect of turning into a useful abstraction, I claim that is not present in LLMs. We need something more. And maybe this will be actually exactly the final frontier of all of this discovery, that like somehow like deriving and like organizing the knowledge once the abstractions are there and once the setups are done, will be done by AIs, but still somehow the insights from the world are the extremely hard part of this whole picture. Here's another example. This is the famous four-color theorem. That's another very interesting thing to proceed. So like, if you try to give this kind of pictures to any kind of language model, without any hint, of course, the language models now are spoiled, right? Because they already have the knowledge about four-color theorem. But we can also train models that don't know this. And there were some experiments also with physical theories. And so far, none succeeded. So they could not come up with this kind of very high-level abstractions. Maybe it's still human illusion that it's somehow like important in any sense. But I think there is something in it that is definitely worth investigating. And this is the last example of the big ones I want to mention, in particular for the following reason, that it was actually formulated by a lawyer, right? Pierre de Fermat was actually a lawyer, and he just observed some kind of curious relation between integers. So there are like many of these kind of relations, but somehow this one catched the most attention because in the 300 years since it was invented, or more than 300 years, it actually, to solve this problem, it took all of the mathematical knowledge. So this short sentence that you have here, which basically completely describes the theorem, took more than 200 pages of extremely dense mathematical text and several thousand pages of preparations with algebraic geometry, representation theory, and so on. So it's like I think this is one of the pinnacles of mathematical and human reasoning. And I would say that in a sense it's different, but it's comparable to general relativity. Maybe in some senses it could be deeper, right? I mean, it's like there are so many different tools used to prove this theorem. And somehow the question again that we can raise is the following, like, if we expose the LLMs to this kind of questions, do we expect them to solve it, right? There are so many inventions on the way that I think it's still not there. Okay, but now let me talk about things that have been done. So I mentioned already formalization. There are, of course, many more theorems that I mentioned that were proved and formalized. Not all of them, of course, but there is a very nice list. If you have never been to this website, it's called Formalizing 100 Theorems. You can actually get a glimpse of what it actually means to formalize a theorem. And I want to show you a little bit of that. By the way, Fermat's last theorem is actually an ongoing project, mostly led by Kevin Bazard, a professor from Imperial College, who is actually really trying hard to organize a group of a few hundred people, basically, that are going to struggle to formalize this theorem. Maybe LLMs will eventually help, but so far it's been very hard. He actually has also a very nice blog on which he describes that, in his opinion, the AI tools, at least for the few coming years, maybe a bit more, are going to be really useful helpers in the sense that they will really make insights, but you should always think of this as a helper, right? You have some vision, you have some precise technical lemma to prove, Everything is on the table except that you might just struggle with time. And sometimes these LLMs are actually able already now to do this kind of insights, but not more. Okay, so difficulties of formalization, I'm going to talk about this in a minute. But now I want to say a little bit more about this automatic theorem provers, what actually lies behind this. So here are examples of how mathematics looks like when it's completely formalized into one of the systems. Let me maybe prominently show you example from Mizar. This is this Polish system from Białystok of Andrzej Trybulec and his group. And you can see that this is some kind of like a mathematical text, except that now it really looks like a programming language. And this is actually a good intuition because it is a programming language. So like every time that I'm going to talk about formalized mathematics, things that there are like hundreds, sometimes thousands or tens of thousands of lines of code that make completely justified claims about the construction of this stuff. And to explain a little bit more, like what it actually means that it's formalized, let me tell you a little bit. Okay, I think I have a problem with zooming in. Oh, okay. About this kind of very bottom part of mathematics, so the formalization itself. So you probably had a course in logic where you were seeing some kind of logical formulas like A implies B, A and B, A or B, and so on. And for doing mathematics, essentially, that's exactly what we do on some kind of very fine-grained level, that we are exactly operating with this kind of rules. This is exactly the complete set of rules of deduction that allow you to completely write every proof like this. But now there is something interesting about this style of doing formally mathematics, is that you have a way, here's another example of a deduction. Usually mathematicians don't write it this way, but in principle, we should be able to do it exactly in the form that you see here. So somehow the final theorem is the bottom line, that this is exactly that kind of convoluted implication. And now on the other hand, and that was an invention of Church in the 40s, is that you can actually replace this classical way of thinking about mathematics as this kind of objects like implies and or, with something much simpler, which is basically based on the notion of a function. And the function in the following sense, that we have a variable or a set of variables, and they have a specific type. And now we are producing something from this variable, and that's another value or some object, and that has another type. Okay, so that's denoted by this notion of the lambda. So lambda x means that x is a variable, L is just denoting the fact that it's a function. Now you have a bunch of descriptions of the type of x. So x colon A is like the type of the x. And then dot m means that after the dot, everything is what is going to be produced, okay? So think about like a quadratic function, like if you take a x squared, like x goes to x squared, then you take as an input a real number, and as an output you get a real number. So these are two types. And this real number on the output is different than the real number usually on the input. That's a lambda function. And now this miracle that Church has observed is that functions can be composed, right? Like you can compose f with g, but if you have a function that has two variables, now you can plug in for every variable two different functions, and then you can compose and compose and compose. So basically everything is about compositionality, okay? And now the miracle that happens is that I showed you now an identical derivation to the one that was done classically in this Gensen calculus. But now the funny thing is that in the end, I get actually something that is an actual function, okay, where the output type is representing exactly the theorem I'm going to prove, okay? So just to give you maybe a little bit more of understanding of what it means, is like, think about the following, that a mathematical theorem is just a collection of steps where every step is some kind of a plug. You have to compose several objects with each other. You just connect them like you'll just compose functions. And to make everything work, you have to connect all the plugs, okay? And in the end, you just get, I don't know, like some kind of lights on your Christmas tree, right? And if it's shining, that means it works. and this type, so that you have like a Christmas tree theorem, that's exactly making sure that you have actually proved this theorem. And now this can be made very precise. This is called the Curry-Howard-De Bruijn isomorphism, which identifies precisely that, that the logical variables are the type variables, so that the types of the object that the functions operate with are exactly the types of logical variables. The symbols are just constructors, formulas are types, and then proofs are terms. Okay, so this means basically that if you're proving a theorem, you're actually assembling a program. And to make sure that the theorem is proved, you just have to have a compiler, so some kind of another program that will verify that the compositionality of the steps is actually working, right? So that's equivalent of, you know, like connecting all the cables and seeing the light is shining, right? The flow of the electrons is going, so that means everything works. So somehow in the end, the conclusion of this correspondence is that mathematics as a formal game, we don't know how we decide on the steps, that's the hard part, but we definitely know that everything that is provable can be somehow reduced to statements which are based on functions. Okay, but now this is very powerful because now if you look at some early examples, and here's one of the early examples of this kind of thinking, this is the famous Robin's conjecture. So that's a conjecture from algebra which stated that a modification of something called the Boolean algebra with a different axiom is actually equivalent to the Boolean algebra. That was programmed by William McCune. He made the program that in roughly 8,000 steps, almost 9,000 steps, completely proved this statement. There was no AI, that was way before AI, it was in the 1990s. And what's surprising is that somehow it showed us that this part of mathematics is not very interesting. It's just like, you know, like if you have a brute force way to connect the plugs, you are going to eventually do it, okay? And my claim is that actually what AIs are very capable at now are exactly this kind of derivations, maybe optimized, but they basically this kind of combinatorial games. Okay, so now let me fast forward now to the year 2023 and 2024. So this is the state of the art. So this is called the Freiman-Ruja polynomial conjecture. That's actually a very interesting effort because it was proved by a very prominent mathematician. Tim Gowers and Terence Tao are Fields medalists. Ben Green and Manners are very top mathematicians. And they wrote a classical paper. So this is actually the statement of the paper written in a very classical way. But somehow before the paper got published, actually before even it was submitted to the journal, the effort of the community of 20 people who helped them allowed them to actually give a completely formal version of this statement of the theorem. So this is the type that I'm presenting to you. But now the type is just something that you have to compare with the statement and say it's okay, right? If you see that these two things are exactly compatible, then now you're just seeking the proof, and the proof was done, and this was actually done still without AI by 20 people, and this is the complete graph of relation between all the theorems, statements, definitions, lemmas, corollaries, and so on. So like, think of this as this kind of Christmas tree. Everything has to be plugged to make this theorem work, okay? So AD 2024, mathematics can be done exactly in this way. How much time? 20 minutes? 15, okay, then I have to rush a little bit. Okay, so let me go forward. Okay, when I move these windows, it becomes tricky. Okay, so I want to encourage you to take a look, if you never have seen this before, at this website of the Lean community to get a little bit acquainted with this strange paradigm of doing mathematics. And why am I telling you this? Because actually there is a very recent project called FizLean, where a group of physicists is really struggling very hard and with already some successes in quantum information to somehow encode big pieces of theoretical physics which can be formalized and proved exactly in this mathematical formal style. Why this is important, I will show you up this in a few minutes. But just remember this name Fizzlean, it's actually a very nice website. And this basically means that everything that you find on this website is completely documented. So if you're ever wondering about the proof of any statement that is actually there, you can actually inspect the proof. There are also human readable versions of the proof. So if you want to encourage your students to take a look, then there are definitely friendly versions there as well. So that's definitely something worth looking at. And here's another experiment. It's experiment. I mean, mathematical experiment in the sense it was a challenge. 2 years ago, Peter Scholz and other Fields medalists asked a group of mathematicians whether they can formalize and document completely the proof of something that he was not completely sure about. And it took them almost 1.5 years to actually do it. So it was a huge effort, but successful. And now I want to finish my part about saying something about AI and the connection between these two worlds. So this will be just like a absolutely fast forward through the history of AI. We definitely should start with the notion of the neuron and of the perceptron of Rosenblatt. These are the absolutely fundamental notions that are still important for this kind of discoveries that we are doing nowadays. But just remember in the foundationally that the perceptron was just made as something that can basically separate two different types of data. It was just that. And now if you combine all of these perceptrons into networks, you can start to separate more layers of data in a more sophisticated way. There is a training process for this. There's like a whole industry of things happening. And now fast forward to 2022 and 2023, we are getting to neural networks of the size that are capable of modeling, at least to some extent, something like a language, human language. And of course, I'm not going to give you a full detail, just to basically glimpse through some important steps of this technical revolution. But I want to somehow talk about the consequences that we are experiencing in the last few years. This is a very outdated chart from 2022, but you can see already how the progression of the size of these neural networks was going. Okay, and the architecture of the neural network with a transformer, that's something that lies behind the successes of the recent auto-formalizations and formalizations and so on. So that's something definitely worth looking at. But now I want to talk about this aspect of language models that is very important for this mathematical discovery, is the fact that these models somehow can mimic programming. And this is the important aspect. And it was already more than 2 years ago that people realized that if you combine a language model with an architecture that you can actually ask the model to generate the tokens in the sense that they generate the steps of the proof of the mathematical theorem, so like every word is like the next step in the construction, then you have actually a very efficient pipeline, because once you have this, you can compile it. And then if the compilation is successful, then you train your network saying like, okay, this was the correct way to adjust the weights, so carry on. If something was wrong, then you still have this back propagation mechanism that was modifying the network itself. This is like a very crude approximation of what is happening. And I'm just saying that somehow this feedback loop is so efficient that you're basically doing two things. You're training the model to be an instructional model, and this instructional model can basically program and do mathematics at the same time. Still in 2023, the networks were very small, and people actually had very little idea about how to generate the training sets. And that was actually a big shock that came in the beginning of 2024, where the group from Google DeepMind developed this system called Alpha Geometry, which was basically trained on zero data, zero human data. Everything was completely artificially generated for the training. And the model, which consists of two parts, of a very small language model and of the symbolic engine that is doing most of the work, was able to derive, so basically prove step by step, very elaborate mathematical constructions in planar geometry. Well, at that time I was quite impressed, but then I realized that, okay, this is not so impressive because Euclidean geometry is decidable, okay? If you have a decidable theory, that means that you just need an optimization algorithm to make it better and faster, right? So that's cool, right? But this is still not all of mathematics, right? It's just a little glimpse into mathematics that is completely decidable. And by the way, we have an actually quite efficient algorithm, which is called the VU method, which allows you to always verify that a statement in planar geometry can be encoded in polynomials. And then you have the elimination theory that allows you to conclude whether it's true or false, okay? You can also use Grübner basis, so there are several techniques. They are super inefficient in a sense. So this is definitely some kind of achievement. But I would say it's still not super impressive yet. I already said a little bit about how this works, so you'll have the slides later, so I'll just leave it for later, maybe for the discussion if you want to talk about this. I just want to emphasize that these constructions were very elaborate, and here's actually how the system looked like from the inside. So like most of the time, the system was actually doing very classical logical, I would say logical envelopes, like making sure what it can prove from the statement that it already got. And just occasionally, it was turning on, triggering the language model to kind of guess the next step. And in 200 steps of the proof, usually the guessing maybe was done in like 5 to 10 steps, okay? So that's not like the language model was doing the bulk of the work. Actually, the bulk of the work was done by the algebraic system called DDAR, so direct deduction algebraic reasoning, that was like custom made exactly for this project. So by the way, if you're thinking now about like ChatGPT, like proving statements, that's exactly one point of the failure most of the time, that you're expecting something which is inherently mostly a language model to do the logical part. That's not how it's done, okay? So like if you ask your ChatGPT to produce for you like a big portion of Python code that you verify and then you see that everything ticks, you can actually turn it into a proper theorem, but not the other way around. So like the language model is not doing actually most of the work here. And now 2025, so we started seeing some kind of very interesting phenomena, like for example, that the mathematical Olympiad was mostly solved by LLMs and then also auto-formalized. And that was a very interesting recent discovery. Now I want to say a little bit still at the end about large reasoning models. So what is the difference between large language model and reasoning model? Well, the difference is basically that reasoning models are the ones in which we also study and promote in the post-training the aspect of deduction. So like the language model just spits the tokens, right? Like just like a Markov chain in a sense. But the reasoning model is the one in which we want to tweak the weights dependent on what is the composition of the tokens. Like, is there like any deeper sense? Like, is there any actually correct meaning in the tokens that the model is producing? And this surprisingly gives you very successful results. And of course, now the problem is that how you measure this. So frontier math was already mentioned. So I took part in this project where we actually discovered that in May 2025, the models that we were testing were not actually very good at doing mathematics. But at the same time, we were very surprised because like this model O4Mini was able to exactly derive completely the solution to this kind of complicated mathematical problem. And now I actually understand a little bit more why. So like somehow my notion of complicated in science has completely been revamped in the last year, because I realized that difficult is not the one which is complicated in the sense of the amalgamation of definitions. That's actually the easy part. The hard part is like how much of the combinatorics and of the combinatorial space of possibilities is at the core of the problem. And that's exactly what delimits the successes in AI in deriving theorems already from the failures. Like if you have a big combinatorial space, surprisingly still humans have some kind of advantage against the model. So like sometimes we just come with some kind of new idea, and that's exactly where the models usually fail. Okay, so I want to finish like last 3, 4, minutes just with some absolutely fresh highlights. This leaderboard is completely out of date, and this was done, I don't know, like 2 months ago, so I should have replaced it. Now we are like at the 30% with GPT Pro. That's already a bit surprising. Still, my exercise has not been done. I would say that these are, I mean, we call it exercises, but these are really mathematical papers. Like we had to really sacrifice, each of us, there were like 30 of us, a single paper. The only thing that the companies see is just the header. So this is like the text of the challenge, not the solution, okay? So it's a genuine challenge for these language models, but we see a progression, like a consistent progression. I would say that it's actually faster than I expected, which is a bit surprising to me as well. Here are some examples, so if you want to take a look at some of these problems, this is actually one that was basically solved. So that's an easy one, I would say. By the way, if you think about the difficulty of these problems, I would say that none of the experts can easily solve more than 2. Okay, so like out of these 50 problems, even if you put Terry Tao in front of these problems, I don't think he'll be able to solve more than 5. Okay, that's the amount of complexity. And the best model currently, the GPT-5 Pro in this 5.2 version, has solved something like I think 13 at the moment. That's quite maybe even 18. So that's the progress is definitely happening. So is this a beginning of the new era? I think in a sense, yes, because I would say many interactions that I do with these models, I do use them as some kind of assistant, even in the sense that they help me to somehow acquire new knowledge. That's a real progress. For the forecasts, I think, well, I don't know if this year 2028 will hold, but I would expect that even this year we are going to see some serious mathematical conjectures being in assistance with humans, completely solved with AI. There are some very new systems, like this is actually from May 2025, so that's already pretty old. It's called AlphaEvolve, which already have improved on some of the human results, like in analysis, in geometry, and in combinatorics. But these are like incremental progresses, but still humans could do this kind of progress. This is something that really surprised me at some points. I do like a lot of these kind of inferences with models. And that was, I think, one of the very first cases where I asked a model a very particular question, and then the model actually spontaneously generalized the conclusion to a completely general statement. That was, I think, for me, the first recorded evidence that a language model spontaneously somehow generalized something out of the blue. So like if we are talking about whether this is possible combinatorially, right, in these models, I think it's true. But the question is like, can we somehow force these models to be creative? That's another question. Okay, so by the way, this is the panorama of mathematics as seen from the inside of the language model. And that also gives you some kind of intuition. So what are these dots, by the way? So imagine that every dot is actually a single paper on archive, okay? And you have a way, this is called the embedding. So you can embed every single paper, like in this reasoning space, as a single place in some big high-dimensional Euclidean space. Then you do some kind of UMAP projection, and then you end up with this kind of panorama, which basically tells you that if 2 dots are close, that means that like semantically these 2 papers are basically very similar. And I was very proud like a year ago that I know so much about mathematics that I said like, wow, I was in so many places. Then I went to this website and I realized that all of my work, like all of my almost 30 papers are just somewhere here, okay? So that somehow gives you also the perspective of why these models can be better than us, because if there's a model that somehow can feel or sense, you know, like a few 100,000 papers from all over the place, then they can make all of these conclusions that we cannot actually. Okay, and now let me finish just with a few absolutely fresh highlights. So AI Scientist, that's a project done by Google. There's another one called Sakana AI, which is basically like an agentic system combining several LLMs, trying to deduce some new ideas in science. I would say that the outcomes are, I would say, mixed. So it's not very clear whether it's going to replace people. Definitely not all of these scientists. There are several incarnations of this project, so just pay attention to this and follow, because they might be useful for your work. And of course, the very recent thing is like from October and December, as the Aristotle and the new formalization systems, which allow you to completely formalize like end-to-end the mathematical things. Here's actually a demo. If you go to the website of this Kimina prover, or Numina prover now it's called, you can actually just type something in the box, and then out of the box, you're going to get a formalization and the document that completely certifies that your claim is actually true with a proof. So that's the state of the art in 2026. Here are some examples of mine. So this is something I did as an experiment with ChatGPT and the formalization system. So basically, my input was just this little prompt, and the whole paper and the documentation that validates this paper was completely done with AI. Absolutely no human intervention, except that I made the tea for myself. That's it. And here's another example of my colleague Pata Ivanishvili, who actually used, in this case, Grok, model Grok, to actually find a counterexample to a famous conjecture. Again, like, who is the author? Okay. Here's another thing. It's actually very interesting video to watch about the system called AlphaProof, developed by Google DeepMind. It's basically like an auto-completion for proofs. It's actually already working. Here's Aristotle. This is the one to which you can actually subscribe for free. So if you're curious about how this works, you can go to the website and you'll get immediately access, and you can formalize theorems just to see, even in physics, how this is working. Now my longest auto-formalization that I'm doing with this system is like 9,000 lines. It's actually a paper from crystallography. So I spent like the last 2 weeks trying to completely document just all the steps in the proof, and it's been quite successful. Okay, and just to finish, this is the another project from Math Inc. It was actually documenting the proof of prime number theorem. So that's a very complex auto-formalization, mostly done by computer. Here's a very recent series of results about the famous Erdős problems. There are like more than 1,000 of these. And some of these problems were actually made by teenagers. So I was helping a 17-year-old from Geneva who came to me on email in December. I encouraged him to just experiment, and he basically proved with ChatGPT and lean auto-formalization in Aristotle one of these open problems of Erdős. That sounds, I think, quite impressive on the side of technology, but also of the persistence of this young gentleman. Okay, so this is the scheme of how the auto-formalization works. So you start from the prompt, you get some kind of hallucination from ChatGPT, and then you formalize it, and then you have a complete document. You're done, you can publish. That's the state of the art for rather non-trivial mathematics, not still foundationally shocking, but quite efficient. Okay, here's another example that I did like a few weeks ago. Also another problem in group theory, quite involved, to be honest. I actually had no idea how to prove it, no idea, and the system proved it itself. I was very surprised. Okay, and then there's another problem of Erdős. Just wanted to advertise from December. This is actually a conjecture about some kind of growth of sequences. Again, auto-formalized completely, all done with assistance of the computers. Okay, so I want to just finish with this diagram for some kind of discussion, and thank you very much.
Thank you, Bartosz, for a nice talk and sharing this exciting perspective in mathematics. Yeah, we have some time for questions. Okay.
Maybe I'll come back to this diagram.
Could you comment the accuracy of the results, because you have the table of one of your last slides.
Yeah.
And because these numbers are not very high, as I understand.
What do you mean by accuracy?
Okay, there was something like this. 12% or something like this. No. There was a list of different chats.
Oh, you mean like oh yeah, I see. You mean like a comparison of the models. Yes. Well, I would say that, like, frankly, to do serious.
So this accuracy, excuse me, 12%. So it's something that we should believe it is useful. Okay, there are different
now it's
Okay, but let me finish my question, because I'm using sometimes ChatGPT, checking some material, and so of course I am observing hallucinations, and I need sometimes to decide: are my costs of checking the results larger comparing to what I'm receiving or not? So what about mathematical proof? Because imagine you are receiving proof that is very long, and can you be sure that this is correct or not?
So first about the numbers, the actual numbers are now like 30%. And what this 30% means for the best model, it means that the model completely solved, or like essentially solved 30% of the problems. Not like 30% of every problem. I mean, if it didn't come up with the right solution, it's not considered. So it's like really like the capacity of these models is like at 30%. Some of these solutions, because we get insights from these companies about how they look like, they are mostly okay. What we were really surprised to see in some of these instances, especially with GPT Pro, is that actually the solutions by the model were different than the one that we designed. And that was very surprising. Now about the details and about checking, that's exactly the answer, this part. So I don't care about whether the model is giving me, you know, like an almost okay proof or not here. Okay, this is basically like how the ChatGPT would argue. But I care like if I have the second ingredient, this formalization part, the second language model that produces the completely documented code, then I'm okay. All right. So like somehow like it's like, you know, like with a scientist that you can make a lot of mistakes on the way, but if you somehow in the final version you write a completely correct proof, then your scratchpad is not important, and somehow the ChatGPT is the scratchpad. And that the important part is actually this formalization process, and that's happening in the last few months. Okay? So most of you have not seen this, and that's why I encourage you to either go to this Kimina or Numina prover to the website, or to actually try this second one, which I advertise here, the Aristotle, because here you are going to see that if you submit your tech file, maybe for the first time, don't submit something that has more than 5 pages. Like try with something even, you know, from the high school level. Just try to submit some kind of, you know, idea. You have a statement, you have a proof, and now turn this statement into valid formalized system. And that's exactly what is going to happen. There is a little subtlety here. The subtlety here is that now the problem was just delegated in the sense that now you have to be completely sure that the informal statement of the theorem that you're trying to formalize is one-to-one with the exactly this theory type that you formalize. And one example, very simple, is the following. Like, imagine you're trying to prove that a complicated matrix of size 10 has determinant 1, right? And now, depending on whether this matrix is defined over a field with 2 elements or over integers, the proof will be different, right? So somehow you need to make sure that the auto-formalizer, like if you wrote in the statement that this matrix is defined over a field with 2 elements and prove that the determinant of this matrix is 1, then you're going to you compare the statement and you see, okay, field F2, the matrix of dimension 10, all the digits are correct. And whatever happens in the proof, you don't care because the statement is correct. And this logic of Curry-Howard correspondence tells you that if this is compiling in the compiler, that means that this is a correct proof, okay? So this is actually quite a shocking perspective because we can get, in principle, in the future, we don't know when, but it's likely, to the proof of Riemann hypothesis, where we definitely understand the statement, we have no idea about the proof. The proof just works, right? It's like there's an example from the theory of automata, cellular automata. There's this automaton called the Langton ant, where you just, design 2 rules that it's like an infinite square grid, and the ant is like this active actor, and if it's on the black tile, it just turns left, change the tile color black to white, and then it moves forward. If the tile is white, then you turn right, and then you move forward, and you just carry on. And actually, the non-trivial statement about Langton ant is that after 10,500 steps, roughly, there emerges a sequence of 105 moves, which allows this automaton to move progressively along the diagonal. And now you can say, this is the proof, right? I mean, you made the computation, and after this 10,000 steps, you just certified that this is the behavior, the global behavior of this Langton ant. So in a sense, you can push all of mathematics to this kind of logic that, in the end, you'll have a brainless proof. Now, I think this is the horror of future AI and human collaboration, that we might get to the level that the AIs will be designing new physics, new mathematics, in which everything will be certified, but we'll have absolutely no idea into the insights of why these compositional functions are actually working. Like, we'll get a rocket that will land us on Mars, but we will just know that it just landed, right? And then we'll be just gracious to, the AI gods or whatever, that it actually happened, but absolutely no clue about why this is working, right? So somehow I would say that this is my fear about the future, that like, if we delegate all of the thinking, it's possible to make it completely concise and structured, but somehow we'll lose insight. And that's the cost, I think. That's a serious cost. I don't have any good answer about this. But I think that the push of the industry, like, I don't know if you followed the news, but yesterday it was announced that SpaceX bought actually this company XAI, which is developing this model Grok. And there is a purpose, because they are actually going to incorporate XAI models into the development of the space rockets and to the colonization of Mars. So I can definitely see the vision that in 40 years, AIs will be mostly busy on Mars, not on planet Earth.
So I have a few questions. Like the first one is like so very quick. Like as I was your student before, so my gentle query is like about, because you have like background in number theory. So what are the breakthroughs, the SOTA like approaches maybe to the zeros of zeta Riemann function, and what is the landscape of that?
Well, I can just say, I mean, very vaguely, I'm mildly involved in this, but it's still like NDA, top secret, blah blah blah. If you want something interesting, you should look at these guys. Okay, so like basically, they are amalgamating the knowledge, and they are actually paired with Terry Tao. This is actually public knowledge, and there is some rumors that Terry has some idea how to harness his, I would say, ideas into these systems to delegate most of the work to AI. But I think we are probably the closest with Navier-Stokes. There are several competing groups that try to solve the Navier-Stokes problem. And I mean, it's hard to say because, it's research, but some people speculate that this might even happen this year. I think I made the bet with my colleague that it will definitely happen until 2028. Maybe I'll lose the bet, but somehow the vibes are really that at least two groups are very seriously into. Well, one is into showing that there's a counterexample, but that's again very hard to predict because you have to construct it. But there's like a lot of things in the game also with different AI systems, not LLMs, that is suggesting that we are very, very close. So but it's mostly human-driven. It's mostly human-driven.
So the second question is like, because LLMs are usually in distribution, great in doing the stuff in distribution. Have you seen like the evidence like the LLM is generalizing to like the out of distribution data, so getting some new mathematics, new theorems?
Frankly, no. That's exactly what I said about the landscape. I mean, I think from my perspective, 100% of the things that looked like generalizing out of the distribution was just basically this picture. Where's this? This picture, it was generalizing out of my scope, not out of distribution. You see the difference, right? And I mean, still useful, right? It's not like concocting new science in a sense. I think this is kind of, this is where the opponents of LLMs are quite to the point that we have not seen going really out of distribution. But like this technology is so on the verge that, when Transformer was developed in 2017, nobody expected these things to happen. And there are new architectures now around the corner. So the main problem is like how they are going to scale up. Like there are so many ideas, but most of the ideas are just not scalable. And that's the main problem with them. So, but I do expect that so far, nothing that we have seen was actually out of distribution. Maybe just, like combinatorially by randomness, but not something like intentionally.
As you expressed some reservations about having people having enough insight as compared to the results of this obtained by artificial intelligence, I am just taking care about producing more people with insight. I'm teaching in primary school. And I taught physics, but then realized that they lack logical reasoning. And so I introduced a new subject, which is thinking. And now try to teach 6th graders, 7th graders logical thinking or satisfaction from insight using primitive tools like Gemini Free and GAMS, which is their name for assistants, AI assistants. And now it seems that it could be quite successful actually at that level. I taught 6th grade class Sudoku using, by generating an assistance to every one of them, which they could use somehow personally in one-to-one scheme. And now this is a very important, I understand that scientists want to win a prize and be the first, but increasing by 10% a number of people capable of logical thinking and deriving satisfaction from insights could radically, I believe, change the future of humans simply.
No,
now, what do you think about it? Because there is a lot of dollars invested in this way, what you have said, but there is another aspect of that. And very often some people who have, completed pedagogy on university try to do so, but unless you are a former scientist and you don't know the effort and the pressure and the final satisfaction of gaining insight, you cannot, in my opinion, configure this in a proper way. And this is also very important, not only obtaining a few more fantastic theorems nobody have predicted before, but just to raise human awareness of the value of insight, using tools based on artificial intelligence.
I would say I absolutely agree, but I think this is one example, by the way. I wanted to show you something like exactly along the lines that you have. So I wanted to actually understand by myself a little bit more how these automatic theorem provers work. So I generated for myself, like a Python code that kind of like does like a hands-on version of what all these, super systems do. And I gained insight from this. And what you said, I think, is kind of hanging on one aspect, which I think is very difficult. It's like the current state of education, not only in Poland, I think it's worldwide. It's so I'm teaching also students, but also teachers in the courses. Most people are so unaware of like how important is to actually exactly what you said, gather this kind of appreciation for the insights from the very early age that like it's amazing because like we end up the kindergarten where like everything is about insight, about discovery, and suddenly we go into the primary school and high school where everything is about the final score, right? And it's like completely killing all the idea for the insight. And I think the places in the world, like Estonia, for example, is one of these major places where the government has realized that the insight is the core foundation of the education. And I think this is exactly what should happen in Poland. That like if we completely switch gears to insight education, we are going to have humans that will be capable of doing some new insights in this new world. Otherwise, we will just get obsolete. And I'm very happy that you mentioned that you're doing these experiments because I don't know many teachers that are actually doing this kind of thing. So this is like very much appreciated. But I think we need a big discussion, and like our government is like very far from any kind of positive conclusions, unfortunately.
I think we need, even though the topic is very interesting, and myself I will have maybe 5 or 10 questions, we need to conclude for the interest of time. But thanks, Bartosz, again for coming.
Thank you.
And amazing talk.